All right. So let us proceed further and try to understand more on whatever we have done. So we have discussed about convolution neural network, and today we are expected to run the code pertaining to that. So first, I am going to go to AI Sprite. Okay, and we shall sign in and get to assignments. Okay, and here, let me go to the slides, and we have convolution neural network. Okay, you have all the CNN related slides. Obviously, it should be there. Why is it not showing up? Yep. We have the data and we have the Python code. No, okay. So let me download the Python code. Let me extract it. And let me go to this code. Let me open, yeah, anyways, Google Colab is open. Let me open a new notebook. Come on, why is my internet slow? I'm not sure. Okay, anyways. So here, I'm going to change the runtime type to GPU and save it. And let me connect. And we will import TensorFlow. TensorFlow is part of Google, right? Google has developed TensorFlow. So already these will be pre-installed. You need not once again install that. So here we are trying to import TensorFlow as TF. And then we are trying to test whether GPU is available or not. And it says true, that means GPU is available. The next line of code is we are going to import the required libraries. Keras is part of TensorFlow from TensorFlow version 2 onwards. Then we have the sequential model that we are creating, in which we are taking the input data set. Okay, we are going to deal with MNIST data set, which is a data set which contains handwritten digits. Okay, this MNIST data set contains, a lot of handwritten digits, and MNIST stands for Modified National Institute of Standards and Technology. Okay, and this data set contains images, handwritten images, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, until 9. And we need to look at each and every handwritten digit, not printed numbers, handwritten numbers. And you need to classify whether that is 0 or 1 or 2, etc. You need to classify in that way. So you have the data sets, okay? And all right. So each and every image is of size 28 by 28 by 1, meaning you have 28 rows, 28 columns. 1 means it is a grayscale image. or a black and white image. Okay, it's a grayscale image or a black and white image. 3 means it is a color image. So now we have grayscale image. 28 multiplied by 28 would give you 784. That's the size of your input layer. And then you're connecting it to 32 different convolution layers, which are of size 3 by 3. And you're using ReLU activation function. Okay, suppose that you're connecting that to a layer which is max pool. 2D means it's a 2-dimensional image. Convolutional 2D means you're having a 2-dimensional image that you're dealing with, 2 by 2. And then you're connecting it to conv 2D. 64 layers is what we are using. 64 different convolution layers of size 3 by 3. And we are using ReLU activation function. And that is being connected to max pool 2D, which is of size 2 by 2. And then you're connecting it to convolution 2D. You have 64 convolution layers of size 3 by 3, and you have ReLU activation function. Then when you say model.summary, you get all the various ones. So let me run it, rerun it. With the original size, yeah, fine. I think it's not taking up. Anyways, we have convolution layer, we have max pool. Remember that max pool has 0 parameters. And why 320? Because you're having 32 3 by 3. If you have 3 by 3, then you'll have 9. If you have your input layer, which has 784 neurons, because that's the size, even if you multiply these numbers, 28 by 28 by 1, you get 784. You're connecting those to 9 plus 1 bias. 1 bias also would be there. So 9 plus 1 is 10. 10 into 32 will be 320. So that is how the number of parameters are given to you. In total, there are 55,744 parameters that your model is going to learn. So let me open another. Oh, where did that go? Okay. So we are now adding, we are flattening those. Flatten means, if you look at the last layer, convolution layer, it is giving you a dimension 3 by 3 by 64. But when you supply your features that you learned from the last convolution layer to your dense network or fully connected network or multi-layered perceptron, etc., you need to ensure that these are in single dimension. So 3, 3, 64, you have to multiply those and then you get a single dimension. Take that single dimension or you'll get a single number. Those many neurons will become your inputs to your dense network. And in dense network, you're saying that you want one hidden layer with 64 neurons and you want to connect that to output layer with 10 neurons. Why 10? Because it is a handwritten digit, right? Either it could be 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. It could be any of these 10 numbers. And you're using softmax as an activation function. Softmax activation function is being used. And for each of these, you get the probability values out as output. And you choose one which has the highest probability. Okay, so let me run it and look at what happens now. You flattened it and you got so much. That is nothing but if you multiply these, 64 into 3 into 3, you get this. Right? And then those are connected to another 64 neurons. Those are connected to another 10 neurons. And the total number of parameters happen to be 93,322. And now that you have created your network, let us import the data set. Okay. And then we'll do some pre-processing. So we are importing MNIST dataset, and from Keras utilities, we are importing something called as two categorical, which would actually convert the data into one hot encoding format. You're loading the data, and within Keras, this specific dataset is already split into training images, training labels, test images, test labels. Already that part is done. So when you load it, that is how it gets loaded. So you load the data set. Then you're saying training images, reshape the images. You have 60,000 images, reshape them into 28 by 28 by 1. And once you get the reshaped images, you're ensuring that each and every image is of the same shape, number one. Okay. And then you're saying convert that into float format. Why do we convert that into float format? Just to help you understand again, you have the inputs which you supply to the input layer, and then you have your convolution layers, and the connections are the weights or parameters that you get could be in float, not could be, they will be in float format. Decimals are allowed. However, the inputs that you provide, if they are in integer format, integers multiplied by float, it throws error. Okay, since it throws error, we need to convert the inputs also into float format, because you can only control inputs. You cannot say that weight should be converted to integers. Such a mechanism doesn't exist. So the only point or the only place you can control is the inputs. So you're converting inputs into float. And then you're dividing it with 255, because you know for a fact that you're supplying images as input, and images have pixels. And each pixel value ranges from 0 to 255. 0 means black, 255 means white. And then you're also taking the output, which is training labels or test labels, and you're converting them into categorical format. You're converting them into categorical format. When you say two categorical, it actually takes these labels. So if you have labels as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, if you have the numbers, handwritten digits in that way, in your database, you will have output variable and input variables. You'll have 7, 8, and 84 inputs, because each image is of size 28 by 28. 28 multiplied by 28 would give you 784. Those many inputs you'll have, and in the output you'll have 0 or 1 or 2 or 3, so on and so forth. This part, we need to do one hot encoding. When you do one hot encoding of this, of only the output variable, then you get 0, 1, 2, 3, 4, 5, 6, 7, 8. And then you also have 9. Okay, you have all these variables. And if the first observation is 0, you put a 1 there, rest all will be zeros. If this is 1, you put 1 there against 1, and rest all will be zeros. So on and so forth. This is called as one hot encoding. And why do we need this to be in one hot encoded format? Because when you want to calculate loss, usually the loss that we use here, since you have multiple categories, you use categorical cross entropy. Okay, and when it comes to categorical cross entropy, you expect the outputs to be in this format. Because, I mean, this is the actual data. So your actual outputs are these. If this is 0, you have 1, 0, 0. If this is 1, you have 0, 1, so on and so forth. You have the actual inputs in this manner. Then you'll also have predicted values. You'll have how many predicted values? 10 predicted values. So if I were to show you the table, 1, 2, 3, 4. Okay, in this way. And you'll have your numbers, right? 0, 1, 2, 3, 4, 5, 6, 7, 8. Assume that this is not there. Then if you have your actual values, I'll call the actual values as P. Say you have a number 0. So again, 0, you'll put 1, rest all will be zeros. And then you have the predicted values. Let me call predicted values as Q. There is 0.9% probability that it could be a 0. There is 0.01 probability that it could be 1. There could be 0.002% probability it could be 2. 0.01 probability that it could be 3. That way you have the probability values. And if you want to calculate cross entropy, just say summation of I equal to 1 until n minus pi into log of qi base 2. Pi, yes. Since you have 10 classes, you write it as summation of I equal to 1 until 10 pi into log of qi base 2. When you substitute I equal to 1, you get P1 into log of Q1 minus so on and so forth, right? You can expand it. And then you can substitute these P values and Q values, multiply to get the loss. But to calculate cross entropy, I need the actual output to be in this format, 1000 format, one hot encoded format. Only then can we apply this format. Hence, we are converting the labels, which are nothing but target variables or output variables, into categorical format. Done. And then we run this. And now we are compiling the model. In model compilation, you're saying loss equal to categorical cross entropy, and you're saying I want to measure the metric, which is accuracy. And then you're fitting your model. Model.fit inputs and output. You're trying to run the model with 5 epochs and batch size is 64. Okay, once you fit the model, you might want to evaluate the model. So let me first fit the model. So all the various epochs, it's gonna run now. Is it connecting to GPU now? It shouldn't usually take so much of time. Is it CPU? Did we select GPU here? Strange. And what am I using here? Ah, my God. Okay. Sorry. So I'm using the free version. Okay, I'm using the free version. It's in Innodatatics, so that could be the problem. Okay, that's okay. Let me complete this part. And then you're testing. And when you tested the data, when you trained the data, accuracy of your training model was 0.99. And when you evaluated your model on the test data, accuracy is so much. If you say verbose equal to 0, it would give a silent execution. It won't show you anything else. When you say verbose equal to 1, it will show you the status bar. If you say verbose equal to 2, it would give you additional information. Okay, that's it. How much time is it taking, minutes and all that, seconds. Okay, it took 2 milliseconds. So fine. That's how we run it. Now let me save this as IPython notebook. Okay, now what I'm going to do is I'll switch this to 360DigiTMG because I have Google Colab Pro available here. This makes it interesting because I can show you how fast it could be now. So let it load. There we go. So I'll go to runtime, change the runtime. Yep, GPU is there. Let me choose a high RAM. Let me connect it. Yeah, if there are far too many sessions, we shall terminate. That's okay. And we shall connect to this. Well, let me run. Once it connects, it'll be faster. Yeah, you have all the modules. Now I'm gonna import the data set, do the data pre-processing, compile the model, and fit the model. Okay, let it come up. For GPU to be assigned, it's taking time. I think the same processor got assigned again. That is why it is taking time. Otherwise, it should have been real fast. Okay. So it's taking 15 seconds, 5 seconds, etc. Here, how much time did it take? Oh, 4 seconds. So the free version was even faster than the paid version, unfortunately for us. Now let me change this runtime to TPU and see whether it is going to be faster or not. It's now going to connect and then assign a TPU machine. TPU machine means obviously GPU also would be there. Oh, GPU is not being taken. Okay, fine. That's absolutely fine. Because we have assigned TPU. I thought GPU also should be there, but unfortunately, we do not have one. Let's see. I just want to experience and see what happens if it is a TPU machine. Would it be faster or not? I think it is taking more time. 11 seconds, the first epoch. So the time taken for the first epoch is less, but for the second epoch, it's 10. So I believe GPU, that too on a free version, is much better. That is all I can infer from this. Very, very against my thought process. Paid version would actually give you a higher RAM and a better GPU, but then that's not the case here, but that's okay. TPU usually is faster than your GPU, but I'm not sure why it's behaving this way. Maybe all the servers are getting utilized. All right. One more thing you should have observed is that accuracy drops when you have a low configuration server on which you run your model. Okay, so this is your CMN pertaining to data science training. Okay, and we have used what? TensorFlow Keras. All right, so now this part is done. This I can anyways close because it's from some other. Now what we shall do is we shall run the PyTorch code. So let me open the notebook, which is PyTorch CNN. And let us execute the CNN part. So we are going to once again use the same MNIST dataset. Let me ensure that I change the runtime to GPU high RAM save. Let me connect. So this MNIST dataset, let me terminate the previous sessions and let me connect now. At any given point of time, you can use only one session. Okay. If it is Google Pro, if it is Pro Plus, you can, yes, certainly use many more. So here also we are using MNIST dataset, which contains list of handwritten digits. And in this dataset, when you load, contains 60,000 training examples as part of your training data. And it has 10,000 observations pertaining to test data. And all the images would be of size 28 by 28. And these are grayscale images, so 28 by 28 by 1. So you're importing the various libraries, Torch, neural network as NN. There is functional neural network capabilities, optimizer, data loader. Torch Vision is used to deal with image related, activities, and you're importing the data sets, etc. You're importing Matplotlib. So what happens usually is, or what is going to happen here is, you take the input image. Okay, you're defining a class neural network module, ConvNet neural network module. You're defining some initialization, you're calling it a cell. And here, all we are doing is, we are creating sequential network. Then how this network works? You're trying to have, okay, let me do this, okay. So we are trying to initialize, basically, when you say initialize, this function defines the core architecture of the model. That is, all the layers with the number of neurons at each layer would be there in this function. So this function defines the core architecture. Architecture means how many layers do I need to have, so on and so forth. Okay. Then you are also defining a forward function. As the name suggests, it will do a forward pass. If you have your network like this, it will do a forward pass. Hence, you have all the activation functions at each layer. Okay, at each layer, what activation function do you need? ReLU activation functions. And we are also using pooling, max pooling. Okay, and even if you want some kind of a dropout, those also will be here. Okay. So you have dropout functions which are defined here. But those are getting stored in these, and those are getting called here. So that means your activation functions, as well as pooling or dropout, which is used anywhere after any layer, that information will be here. And we are going to call that as a prediction of the model. Okay, the final layer is called as a prediction of the model. So let me go like this, yeah. So the output layer gives you the prediction, which has the same dimensions as the target output. The actual output which you have in your data set is called as actual value or target value, or it is also called as ground truth. Okay, it is also called as ground truth. And here, the first convolution layer has one input channel, one channel input, 16 channel output, kernel of size 3 by 3, that means stride equal to 1. The one channel input is essentially saying that it's a grayscale image that will be fed into the model. And 3 means 3 by 3 is a kernel size. Kernel sizes are usually odd numbers so that the input image pixels are symmetrically distributed. So that's what we do. 1 by 1 would be too small. That means every pixel would be analyzed. That's why we are taking 3. Odd number means 3, 5, 7 in that way. 1 usually you don't consider. Okay, so if you have a 28 by 28 image, you cannot say that, sorry friends, extremely sorry. We cannot say that 27 is also an odd number. So we can as well do 27 by 27. We could have done that, but no, we are not doing that. Okay, so that means entire image is being utilized completely. You're trying to extract. That means you're trying to get a coarse grained features. That means features from the entire image almost, right? If it's 28 by 28, and if you're using 27 by 27, then almost that filter applies on complete image. That won't give you good results. Instead, I mean, you know, most important features, visual features in an image are local, and they can be captured using small kernels. So 3 by 3 seems to be a fairly decent bet. But you can experiment with multiple things. You can also experiment with 5 by 5 and the number of channels in the output of the convolution layer is usually higher. Okay, or it will be equal to the number of input channels, at least 28, because you have an image of 28 by 28. So our first convolution layer takes one channel data and outputs 16 channels, right? One-dimensional image, or not one-dimensional image, sorry. It's 28 by 28 by 1. So this one is being taken, one channel. And if you apply 16 3 by 3, you'll get 16 different channels as output. So that means this particular convolution layer, which has 16, right, is trying to capture 16 different outputs, 16 different kinds of information from the image. Each of these image, if you have 28 by 28 by 1, if you have 3 by 3 filter, if you're applying 16 such 3 by 3 filters, 3 by 3, 3 by 3, 3 by 3, that way 16 filters, each of that would give you some interesting output, right? And that's called as a feature map or a response map. Okay, or activation map. All mean the same. These different terminologies, I request you all to please remember. We can increase the number of channels. Okay, and here what we are doing is, since we have 16 channels, so if you have 28 by 28 by 1, if you're applying 16 3 by 3 filters, then you'll have 16 layers coming out. So you're taking those 16, and then you're applying 32 3 by 3 filters on that. So output will have again 32. At this layer, you'll have 32. Okay, and finally you see 1, which is nothing but stride equal to 1. So we are ensuring that the kernel size is 3 by 3 and we are striding it by 1. Whatever is at stride, those many times it gets moved ahead. And then you are giving dropout, which we have already discussed. And then we are connecting that to a fully connected network. Okay, rest all is pretty self-explanatory, wherein you're defining yourself, you're applying the CNN here, then you're applying activation function, then you're taking this, then activation function. Then you're applying max pool, then you're applying this dropout, then you're flattening before you supply the data to your fully connected network. So this is your CNN base. Whatever you get from your CNN network, you take that and supply it to your MLP, which is called as fully connected network or dense network. Then ReLU, then dense network, dropout, then the fully connected network, which is nothing but the dense network. Okay. So here, typically at this stage, you'll get an output which is a 12 by 12 by 32 dimension. You're ensuring that you multiply those to get a single dimension. So that's called as flattening. So when you flatten, you want this to be in single dimension because your multi-layered perceptron expects input to be in single dimension. Okay, that is what we are doing. And then let me run this part. And then you are applying softmax to the final layer, returning the output. Why? Oh, I'm sorry, I didn't run this. Okay, and then we have a back propagation step which is going on, and we have Optim. Optim here, you have Optim here. Basically, we have torch.optim module. Let me show you that. Torch.optim. This module performs backpropagation. So this particular code that we have written here, rather than going line by line, I'll just tell you that. We are taking our data, okay, we are assigning to a device, all right, and then we are initiating with 0 gradients, that is random initialization, and then you get the predicted values from the model. You compare the predicted values with the actual values to get the loss, and then you backpropagate. Okay, and then optim.step means you want to optimize now. That is, you want to minimize the loss. And here you're saying print the epochs after every 10 iterations. Okay, that's a kind of code that we're writing here. So let me run it. Okay, this entire process is done for only, and this entire procedure is done once it qualifies as 1 epoch. When the entire data set is read once, it's going to give you the output. Then here, a similar kind of routine is written. The only difference is that here, the loss is computed from the predictions, model prediction and the actual value, but it is not used to tune the model weights. You're not going to tune the model weights based on this. Instead, the loss is used to compute the overall test error across the entire test batch. Let me run. So here there is another, a thing which is called as data loader from Torch module. And these lines of code, datasets.mnest, etc., whatever is written, it will just extract the data, but it is doing a lot of pre-processing. Here we are mentioning various things such as batch size. Okay, what batch size do you want to select is something left up to you. A very small batch size can lead to very slow training. A very large batch size on the other side also might slow down the training due to long waiting time, which goes into calculating all the gradients of all the batch size entries. If you say 256, all 256, it needs to store first. That takes time. Okay, then for both training and test dataset, we specify the local storage location. Okay, where do we want to store the data? Local location we are specifying here. Okay, we are also specifying that we want to convert the data into tensor format. We are also specifying that we want to normalize the data. If you take each value of training data set, average of that and divide by 256, you're getting this much. If you are going to take the standard deviation of the entire training data set and then divide by 256, you get this. And that's how you're normalizing the data. Okay. So we are doing this for, this is, I think, the same line of code again. Not mistaken, let me remove this. Okay, once it is done, you're here specifying on what device you want to use. We are specifying that we want to use CPU. You can also use GPU. We are just specifying that we want to use CPU, we want to use convolution neural network, and the optimizer that we want to use is ADA delta. And we want to use the default parameters and learning rate as 0.5. I mean, these are all experimental stuff, so you can choose whatever you want. And we are saying that we want to run the model for K epochs, that is 3 here. So let me run it. Once you test the model, train the model, you also want to test it. So now training is going on. And after every step, you have the training loss. Epoch 1 is going on now. Then after epoch 1, you'll have epoch 2. Mind you, we are using CPUs. When you use CPUs, of course, it will take some time. You can as well use a GPU, but I just wanted to show you how a CPU machine works. So let it complete. Okay, it's done. So now what we shall do is, here, why is it running for only 2 epochs? Because in Python, indexing, the way it works is the last value is ignored. If you want 3 epochs, put this as 4. So range of 1 to 3 means 1 and 2, the last number is ignored. Now here, you're, testing on the test data. Okay, you're taking the test data, and then you're seeing what is the first image in the sample data. You get to see that it's 7. And then you're printing out the results. Model prediction is 7. And the ground truth is also 7. Right? When you use your model and test it on the test data, it says the predicted value is also 7 and the actual value is also 7. So here ends the story with respect to PyTorch CNN. Now let's get into RNN, recurrent neural network. And let me go to RNN slides. And here we go. Okay, so there are quite a few things that I think I need to hide, but then I'll do one thing. I'll go to AI Sprite and then go to RNN network. Break, is it? Okay. So, all right, that's absolutely fine. So let the slides come up. Let me see whether we have all the slides listed down. Yes. Okay, I think we have the right amount of slides. Shouldn't be a problem. Okay, so we will get started now with recurrent neural networks. So we discussed about ANN. We discussed about ANN MLP, which is also called as fully connected network or dense network. So we understand how to handle the structured tabular or columnar data. Then we have looked at CNN, which is used to deal with images. And now we have recurrent neural networks, RNN. So let's proceed further with RNN. Recurrent neural networks are used when you have sequence data. Sequence could be sequence of words or sequence of sounds, or if you want to convert the data from one language to another, there are also sequences involved. Sequence of text. And when you have sequence of data, you can also deal with time series, or that is also called as time series data. If you have time series data, then also recurrent neural networks can be applied. Okay, so maybe you want to predict the next word in a sequence. Foreign, next word should be minister, maybe. Right, so when you have such sequences, you use recurrent neural network. When you have sound, when someone is talking certain words and suddenly some words you could not hear properly, then recurrent neural network can be used to rectify that so that you hear the right sound. And RNN is also used in machine translation, or language translation kind of problems. And this is all about converting one language to another. If you have some text written in German language, and if you want to convert that into English, then also recurrent neural network is used. And if you have words which are in a certain sequence, those words need not be exactly in the same sequence in English. For example, something called as bring in, right, is called as return. right? Bitte is called as please. Das is called as the. Auto is car. So, but this is the first word, but it's second word when it comes to English language. So this is the third word when it comes to German, but it is the first word when it comes to English. So the sequence might vary. Okay, so recurrent neural network is used whenever you have these kind of sequence data or time series data. Having said that, we have a lot of language models and a lot of use cases are resolved using that. What is a language model? A language model computes probability for a sequence of words. It will give you the probability on which word should come next. After a sequence of words are used, which word should come next? And they're very useful for many tasks, such as next word prediction. Stocks plunged this morning, despite a cut in interest rates by the Federal Reserve. As Wall Street. As Wall Street. Okay, street would be the next word. Then it is used in spell checkers. They are leaving in about 15 minutes. Minutes is incorrectly, typed here. So this would be highlighted that this is incorrect. Because when it comes to different characters, M-I-N-U, after that, the most probable word with highest probability would be T. Then the next word with the most probability would be E. Then you'll have S. But here it is different. Then you have mobile autocorrect. He is trying to find out. It is actually find. So these kind of things are also highlighted because he is trying to find will be the most probable answer or the word, next word, as opposed to find. Then you also have speech recognition. When it comes to speech recognition, you have this. Theater owners say, in speech, say because of some disturbance, it was recorded as unicorn. But you know for a fact that it cannot be unicorn. Theater owners would speak more about popcorn. Why would they talk about unicorn? Unicorn are those, unicorn is a special animal for that case. Kind of very rare animal. It doesn't, we will not frequently come across that. But then unicorn is a word which is tagged to businesses and startups of late. Any startup which crosses $1 billion in valuation is called as a unicorn. Okay. So when it comes to speech recognition, theater owners say popcorn sales have doubled. So it will automatically correct this unicorn to popcorn. And within automated essay grading, if you write any of the entrance exams to write to go for your master's, such as GMAT or GRE or IELTS or TOEFL, etc., you'll also have to write essays. When you write essays, those essays will be automatically graded. Automatically, how many points should we give to a person, right, is something which is done using your language models. Then in machine translation or language translation, also we can use those. And here it will help you in word ordering, word choice, etc. Word ordering means the cat is small. Probability of having the words in this sequence, that is the cat is small. The probability of having the words in this sequence is high in comparison to small the is cat. So the probability of this will be less in comparison to probability of this. Then you also have word choices. You have probability of walking home after school. the probability of this or the words appearing in this sequence will be more than the words appearing in this sequence, which says walking house after school. So the usage of word home is more appropriate and it will carry more probability as opposed to having the word house. So these are the various scenarios where your language models can be used. And we have traditional language models, which is based completely on probability. In English vocabulary, in English language, we have 172,000 words in English language. I'm going to call this as V, number of words. And all these words are individual words, so I'll call this as unigram, single word clouds, unigram. Bigram means 2 words. For example, here you apply the probability in this way. What is the probability that word 2 appears given that word 1 has already appeared? That means, what is the probability that the next word would be language given that the first word was traditional? So you count how many times this word 1 and word 2 appears together, divided by probability of word 1 or count of word 1, that would give you probability. So if you have bigram or bigrams, this count will increase from V to V square. Then you also have trigram models. In trigram, you'll have 3 words. What is the probability of getting word 3 given that word 1 and word 2 have already appeared? What is the probability that you'll get models given that traditional and language have already appeared? For this, you look at the count. How many times did traditional, language, and models appear together, divided by how many times traditional and language have appeared together? That would give you trigram models. When you have trigram, you'll have V raised to the power 3. In that way, you can go on and on. And if you have an n-gram model, okay, if you have an n-gram model, you will have V raised to the power n. Those will be the number of words that would be there approximately. But then, do you have the memory to store those many words when you do the processing? Just as an example, way back in 2013, people used a machine with 140 GB, and it has taken them 2.8 days to build 126 billion tokens. Each word is called as one token. And here, to build 126 billion, it has taken 2.8 days with a 140 GB RAM. In order to handle 172,000, and even if you go with a 4-gram model, means multiply 172,000 4 times. That would be huge amount, and processing that much amount of data requires gigantic RAM. That much amount of memory doesn't exist, right? So that is one key drawback of traditional language models. One is the vocabulary size explodes. If you have an n-gram model, V raised to the power n. V is the number of words in English language. If it is 172,000, then 172,000 whole raised to the power n. Another disadvantage with traditional language models is that it will not store the past words in context. It will not store in memory. And that is very important, right? For example, consider a case where an article discusses about the history of Spain and France. In the first page, in the first paragraph, say the paragraph reads as Spain and France are the two countries in Europe. Okay. And somewhere in the 10th paragraph, the sentence reads as, the two countries went on a battle. The two countries here refers to Spain and France. The two countries mean here Spain and France. But since this information, which was spoken in the first paragraph, was not stored in memory, okay, when the reference of the two countries appears in somewhere 10th paragraph, your model will not recognize that the two countries that are being referred to here are Spain and France. That reference does not exist. Okay, this is also another disadvantage with your traditional language models. Then people thought, okay, if this doesn't work, can we experiment with multi-layered perceptron, MLP? Okay, and then they experimented with MLP to see whether that issue would be resolved or not. So let's see how it works. Say you have 3 words and you want to predict the 4th word. So that is a model that we are building using MLP. So what you do is you get the data from, say, Wikipedia, newsletters, news articles, etc. And you say word 1, word 2, word 3, and say you want to predict word 4. So you say original, neural, language, model will be 4th word. Okay, another thing could be all, conventional, language, models. This could be another word, another example or training observation or row. In that way, you create a lot of rows. And then when you want to train, when you want to supply these, assume that these are your inputs and this is your output. Word 4 is your output and these 3 words are your inputs. When you want to supply the inputs to your model, you cannot supply the words in the raw format. Your model will not understand. Even in CNN, you need to convert your images into some numeric format. If you supply your images as is to your model will not understand. These are all mathematical models, so they only understand numbers. So when you supply these words as is, it will throw error. So what should you do? Say this is the word original, neural, language, model. Anyways, this is output. These 3 inputs you need to provide. So then you do a one-hot encoding. In English language, how many words do we have? 172,000 words. You have 172,000 words. You put all the words, a, and all the words, and you put 0, 0, 0, 0, 0, 0 throughout. Wherever you find this word original, there you put a 1. Rest all will be zeros. Then supply this one-hot encoded numbers as an input here. So what will be the size of this? 172,000 numbers are there, which is nothing but V, vocabulary size. So the size of this will be V. The second word that you supply also will have a vocabulary size of V. The third word that you supply also would have a vocabulary size of V, because you need to convert each and every word into one-hot encoded format. And then you connect it to a hidden layer. Say you have H neurons. For instance, if you have 3 neurons, and if you have 2 here, 1, 2, 3, 4, 5, 6. There are 6 connections, 3 into 2. In that way, if you have V, let me erase these things also. So if you have V, then V into H will be the number of neurons, number of connections. V neurons, H neurons, V into H. For these two also V into H, for these two also V into H. In that way, if you have n number of words, you'll have n into VH. Those will be the number of connections in this layer. Then you're taking it to the next level. Here also you'll have vocabulary size V, which is the output. Why? Every word of English language will be there because you want to predict, given these three words, what will be the fourth word. For each and every word of English language, you'll have probabilities. You'll have probabilities. And that word which with the highest probability would become your output. The word with the highest probability will be shown as your output. And the number of weights which I learned from here to here would be H into your output. In your output, you have say 2 from hidden layer, in hidden layer 2, output layer 2. Then 1, 2, 1, 2, 4 connections, 2 into 2. In that way, number of connections here would be H into V. So the number of weights or parameters that your model is going to learn is NVH plus VH. So this can be written as N plus 1 into VH. So the number of words you have, plus 1 into V into H, those many parameters your model has to learn. These number of parameters are much less than your traditional language models. In your traditional language models, it was V raised to the power N. Here it is N plus 1 into V raised to the power H. One quick thing. While you're watching this, take a book and a pen, write down whatever is being discussed. Whether your understanding or not is immaterial, right? You have to make a running note, and that is mandatory for you to learn these concepts. Number one. Number two, when Python programming is executed by you, Python code is executed by you, ensure that you type each line of code. Okay, please type each line of code. Okay, next. So the number of parameters have reduced significantly. Vocabulary size raised to the power n would make it grow exponentially as in how the number of words increase. But here it won't grow exponentially. But in traditional models, we had a challenge that the previous words were not getting saved in memory, like Spain and France are first paragraph. And when someone says those two countries, then those two countries will not relate to those Spain and France, right? Because the previous words were not getting stored in memory. Hence, okay, sorry, my bad. I need to switch the AirPods. Okay, hope you all are able to hear me. Okay, I just switched. Okay, all right. So, does the same problem exist here or not? To understand that, let me tell you upfront that the previous words in MLP also will not get stored in the memory. Because if you're, say, processing this entire paragraph is broken down into 4-word chunks. Like in all conventional language, 4 words. In all conventional, 4th word is your output language. Then it takes all conventional language models. So all conventional language models now become output. Then conventional language models the. So conventional language models the becomes your output value. In that way, it is split and it is stored here. But all these different sentences or sets of 4 words each are independent of one another. They're not dependent on one another. So the previous words are not stored in memory. So the same problem is here also. In MLP also, you have the same problem. In traditional also, traditional machine learning models or traditional language models rather, we have the same problem. In MLP also, we have the same problem. That problem is not solved. And another thing is, if you do a bigram analysis, it works only when you have chunks of 2 words. On similar lines, for MLP also, it works on fixed window of context. That means if you have built a model wherein take the first 3 words as inputs and predict the output. If this is what you have built, then it works only in those contexts wherein you give first 3 words as inputs, you get the output. First 3 words as inputs, and then you get the output. That's it. It works only on that. If I have 4 words, and if I want to predict the 5th word, it doesn't work. If you have 4 words, and if you want to predict the 5th word, it doesn't work. Because you train your model in such a way that it takes 3 inputs and predicts the output. So both of these, traditional and MLP, works on fixed context, fixed window width. So how do I address these issues? To address these issues, we have something called as recurrent neural network. And in recurrent neural network, you have a setup like this, wherein the challenges which exist in traditional language models and MLP are addressed. Let us understand. I'll write down here. In traditional language model, we had v raised to the power n, the number of parameters. The previous words were not stored in memory. So previous words not stored in memory. And it doesn't work for flexible window width. It works only when you have fixed window width. Then on another side, you have MLP, multi-layered perceptron. When it comes to MLP, multi-layered perceptron, the number of weights would be n plus 1 into VH, a number of parameters. It is much less than this. But these 2 issues, not stored in memory and fixed window width, these 2 challenges exist as is. To solve these issues, we now have something called as recurrent neural network. People experimented and came up with something called as RNN. So let's see whether these issues are addressed in recurrent neural network or not. So say here you have 3 words and you need to predict a 4th word. Okay, you have 3 words and you need to predict a 4th word. You take that word, convert it into one hot encoded format. If you have English language, you have 172,000 words. And if you represent that word in one hot encoded format, you'll have the size of vocabulary as V. Okay, and say you have a hidden layer, H. For now, forget about these, friends. I'll talk about these later. There are different variants of recurrent neural network. That is when I'm going to talk about these things. Okay, so here, number of are H, of course, number of hidden layers or neurons in this hidden layer are H as well. Then it becomes V into H will be the number of weights. And the initial layer that is given here is a dummy hidden layer with all zeros. It's a dummy hidden layer just to maintain consistency. So H into H, okay, those will be the weights here. H into H. This will be V into H. V into H will be the number of weights. Then whatever is learned from this word, that information is carried forward. Unlike the previous architecture of MLP, here it is different. This word, which is going into hidden layer, is carried forward. And you have another word. Again, you do one hot encoding. Size will be V. And here you have a hidden layer with size H. When you multiply these two H, you get VH. And then here you have HH. Plus number of hidden layers H into number of hidden, number of hidden neurons H into number of hidden neurons H. Then again, it is moving forward. When it is moving forward, the information of these two words are also getting carried forward. And this will be H. If you're supplying a third word, once again, you convert the third word into one hot encoding format, and you'll have a vocabulary size B, 172,000 words. That specific word would be given one, rest all zeros. So you have V into H would be VH. Then H into H, right? Hidden layers into hidden layers. Then finally, you have your output layer. This output layer size also will be V, number of words in the English language. For each word, you'll get a probability as an output. And that word which has the highest probability would be the next word. Now let's count how many weights a model is learning. So here you have V into H, V into H, V into H. It will be VH, VH, VH. If you have 3 words, you'll have 3 VH. If you have N words, you'll have N into VH plus. H into H will be the number of weights. H into H, H into H. If you have 3, then you'll have 3 HH, because first one is anyways dummy, all zeros. So you'll have 3 HH. And if you have N words, you'll have N into HH. Plus, in the final layer also, you have V into H. So if I were to simplify it by taking these two, then it'll be N plus 1 into VH plus N into HH. Here in MLP, you have only N plus 1 into VH, but here in RNN, you have N plus 1 VH plus N HH. So the number of neurons are huge when it comes to RNN, more than MLP. Then why should I use RNN, right? Hold on. When your model backpropagates, it will take these weights, and these weights, and takes an average of that. So even if you have N weights and then replaces all these with that average, when it replaces all these weights with that average, all these weights will be the same. So even if you have N words, all will be the same. So it's 1 into HH. 1 into HH will be HH. And then all these weights, also get averaged, and you'll have single set of weights, VH. When you take the average, you get single set of weights, take average of that, and replace all these weights with the average. In that case, you'll have a single set of weights here also. So instead of N will become 1 now. Even if you have N words, you'll have same weights. So N will be 1, 1 plus 1 is 2, 2 into VH. Now this becomes a very, very small, I mean, your model has to learn a very small set of hyperparameters, parameters or weights. So this problem is solved. Next problem is not storing in memory. With respect to traditional and MLP, we had this problem wherein previous words were not getting stored in memory. But here, every word will move on, and every word is getting saved. In memory. Every word will go here, will get carried forward. Second word, that also gets carried forward. Next word gets carried forward. So the words are getting stored in memory. That means the context that Spain and France were the two countries which went on a war in the first paragraph. And in the last paragraph, if it says the two countries, then it is getting stored in memory because Spain and France in the first paragraph, when they get processed, they're getting stored in the memory. Somewhere else, if you say the two countries relates to those. Okay. And the fixed context, if you have three words and predict the fourth word, that problem exists in both traditional language models and multi-layered perceptron. So here what happens is you can expand to whatever extent. If you have four words and if you want to predict the fifth word, expand it one more time. If you have five words and if you want to predict the sixth word, expand it one more time. Or if you have two words and if you want to predict the third word, you collapse it. So expanding and collapsing is also something which is possible. You can expand, you can collapse. How many ever times you want, those many times you can expand, those many times you can collapse. But the challenge is you'll have all the weights, right? All the weights. So all those weights you keep multiplying throughout when you pass on to the network. If all these weights are greater than one, if they initialized as greater than one, and when you keep multiplying those words throughout, those numbers throughout, those weights throughout, then the final number will explode. And that's called as exploding gradient problem. And if all these weights which get initialized are less than one, and when all those weights are getting multiplied throughout, your overall weights will get vanished. That's called as vanishing gradient problem. So you have exploding gradient problem and you have vanishing gradient problem. Okay, so this is what is exactly discussed and it's just put in some format. Okay, so what's happening here is if you have this kind of a network, in this way. So if these are all the various inputs at a specific time period, if this is the current time period, this is the previous time period word, okay, in that way if you have, then what happens is, and say this is your previous hidden layer, this is your current hidden layer. You're currently at this step. Then every neuron will have integration and activation. When it says integration, you'll have the weights between this hidden layer and input of the current time period into this input. So you have weight of H and X at current time period into the input, plus you will have the previous hidden layer into the weights of these two hidden layers. Get multiplied. When you add these two, they get integrated because both are going in, they go into every neuron and every neuron has integration. So it gets integrated. Then you pass on that to the activation function. And finally, in your output layer, the number of weights between this hidden layer and this would be WS into this hidden layer. And in the final layer, if you have more than one, obviously you'll have more than one every time, most of the times. So you use softmax activation functions because because you have more categories, more than two categories. Finally, that means you get some output. So what is the probability that next word would be one of the words in the English vocabulary given the set of inputs would be this output. This symbol just says that your memory is recurrent. It won't go away. It will remain like that. This is also exactly the same representation. There's no change. But the only thing is, if you want to collapse or expand your network, that is, if you want to unfold or fold your network, you can do that through time. Okay, you fold it through time or you unfold it through time. Okay, so that's called as folding or unfolding through time. Expand or collapse. But then if you keep expanding it for too much of time, then what will happen is the exploding gradient problem arises, or vanishing gradient problem arises, because you have far too many weights. What if all the weights are less than 1? If you have far too many weights which are greater than 1, what happens? It will run into truncated, it will run into the problem of vanishing gradient or exploding gradient problem. To solve that, people came up with something called as truncated backpropagation through time. How are the weights updated? Using backpropagation. Here, you move across time. Hence, it's called as backpropagation through time. It's called as backpropagation through time. And the same algorithm that I explained is written in text. So first, you'll have 0 magnitude vector. Then how many words you have? Okay, you take those many words and you pass through your network. You pass through your network. And finally, you get a predicted value. You take the actual value and then you get loss. Given that loss, backpropagate and update the weights. That backpropagation is called as what? Backpropagation through time. And when you backpropagate the weights here, etc., you average the weights, or the weights here and here also you average and ensure that all these weights are identical for the next pass. Next time when you move forward, they should be all identical. Okay, anyways, if you expand too much, then it will run into vanishing gradient problem or exploding gradient problem. To solve that, we have something called as truncated BPTT, truncated backpropagation through time. That means you often say that, you know what, I'll not expand it more than 8 times or more than 9 times or more than 10 times. Put that condition. The good part is when you do that, okay, the good part is when you do that, when you truncate it, you are not running into this problem of exploding or gradient problem. So sorry, exploding or vanishing gradient problem, or you will not run into huge training time problem. The training time will be limited. Very soon you can train your model. But the downside of this is that if you expand, maybe you learn all the patterns. But since you're not expanding, you're unable to learn all the various patterns. Okay. So, of course, cross entropy is a loss which is used. There are many cases, many to many and all that. So now, let me see if all the variants are explained somewhere. No, okay, let me. So there are a lot of variants, friends, such as many to many, one to one, one to many in that way. There are various examples in RNN. Many to many means, suppose you are taking videos and you know for a fact that the specific video is made up of multiple frames of image, and say this is a football match, video of a football match. In the first frame, maybe the person is kicking the ball. In the second frame, it's going into the goal. In the third frame, the goalkeeper is jumping. In the fourth, the goalkeeper stopped the goal. then what happens is each frame, if you provide as an input to your RNN, immediately it will give the results. Okay, first frame, person is trying to kick the ball. Second frame, the ball is going towards a goal. Third frame, goalkeeper is jumping. Fourth frame, goalkeeper stopped the goal. In that way, for each and every image in the video, you're going to give a caption. So it ultimately becomes a commentary. Commentary can be given automatically. When there is a movie that you are watching on Netflix, if you say, I want to see the subtitles, subtitles are also solved using recurrent neural network, because each frame of image and what is it that they are talking would appear as subtitle. So in those kind of scenarios, immediately you display the output, many to many. One to many, if there is an image that you give as an input, you want the caption to that image. So there might be multiple words. Okay, there could be many to one. You have multiple words, you supply all those words as inputs, and output would be whether it is positive or negative, whether the sentiment is positive or negative. Okay, in this way, there are a lot of variants also which exist. Okay, we can also combine something called as CNN RNN. Okay, we can also combine CNN RNN models. CNN RNN models, what they do is, you take the image, pass it to your CNN network, you pass your image to the input layer, then you'll have convolution layers. And after your convolution layers, that is called as convolution base, convolutional base or convolution base, you flatten, that means you make these outputs as single dimension, supply it to your fully connected network or dense network or MLP, whatever you want to call it, right? That's what we have done in CNN models. But here what we will do is, we will extract all the features and we'll pass it on to our recurrent neural network. And recurrent neural network might want to give the caption of this image. So say you take this specific hat, person wearing a hat, supply it to RNN, CNN. CNN extracts all the features and it will give it as an input to RNN. Using some special keyword called a start, RNN will start its journey. It will predict that the first word is straw. Whatever you get here, that will go here as input. Then you're predicting that the next word is hat. Whatever you predict will again go as input. And then it's saying that this is the end. So the name of the hat will be straw hat. I mean, the caption of this image would be straw hat. Okay, that's the exact same thing that is explained here. Here also. Okay. So to work on this image caption, people have used Microsoft COCO dataset, which has 120,000 images. So if you look at the dataset, you'll have the image and you'll have the sentences. Say this is the image. For this image, you'll have first sentence. For the same image, you'll have a second sentence. For the same image, you'll have a third sentence. In that way, for all the for the same image, you'll have 5 sentences, and then starts another image with which will have again 5 sentences. So if you have 120 images and each image has 5 sentences, and 120 into 5, that is 600,000 will be the number of rows that you are going to have. Using Microsoft COCO dataset, people have built image captioning. For example, it has a man riding a bike on a dirt path through a forest. Second caption is bicyclist raises his fist as he rides on desert dirt trail. In that way, you have the data. So whenever you have images, you get the output. A few things might be accurate, a few things might not be accurate. You need to live with that. Then people came up with a variant called as bidirectional RNN. Okay. Before even I get into that, all these videos would be made available to you under the section recommended videos. You'll have something called as neural network. Under the recommended videos, you'll find that. And reading these is mandatory, not optional, mandatory for you to get into deep learning and artificial intelligence program. Okay, so that's one program that I would say would shape the careers of people in a big way. So that, okay, so going back to this, we have traditional RNNs. Suppose there is a sentence which says, for example, Yashwant. Yash was listening to the session. Okay. And or let me put it this way. Having said he will watch recorded video, Yash left the session. Suppose you have a sentence like this. If your RNN would traverse this in this direction, having said he will, now it doesn't recognize that he is Yash because it didn't encounter the word Yash yet. So having said he will watch recorded video, Yash left. So since it's traversing in this way, it will recognize this Yash is a different person. He is a different person. It cannot correlate. Hence, if you have bidirectional RNN, it is going to also read in the reverse direction. If it reads in the reverse direction, what happens? Left, Yash. Now it's encountering Yash. Video, recorded, watch, will, he. The moment it sees he, it recognizes that it is Yash because it already has, processed the word called Yash. And then it is looking at the pronoun called he. So it is going to tag he to Yash. So that is the advantage when it comes to bidirectional RNN. But the disadvantage with bidirectional RNN is that it consumes twice as much memory because it's going to process the words in the reverse order also, and it needs to store all the weights. So forward pass weights, backward pass weights, all put together give you an output. Okay. Then we also have deep bidirectional recurrent neural network. In deep bidirectional RNN, you'll have multiple hidden layers. When you have multiple hidden layers, then it becomes deep. The moment it becomes deep bidirectional RNN, the moment the depth increases, the moment it becomes deep, the capability of learning the data, learning about the data becomes multifold. I mean, it learns a lot of insights. Accuracy of the model will increase. However, the amount of time it takes will increase because a lot of hidden layers, bidirectional, right? A lot of weights, a lot of processing, right? A lot of weights should be saved, and it takes huge amount of time. So those are the things that exist. And of course, you have advanced algorithms such as LSTMs, GRUs, right? Bidirectional LSTMs, bidirectional GRUs, deep bidirectional LSTMs, deep bidirectional GRUs, one-dimensional convolution neural networks, right? And then you have RCNN models, fast RCNN, faster RCNN, mask RCNN, region-based convolution neural networks, which are used for object detection. Okay, and then you have YOLO models. You only look once. These are also used for object detection purpose. We have tiny YOLO and bunch of things. You will have to understand how to use pre-trained models, because when it comes to processing images or textual data, you need pre-processing. This is with respect to images. Then you'll also learn about explainable AI concepts such as GradCam, etc. All these you learn. People who have enrolled for professional program will learn all that. Then with respect to processing text, these are all NLP techniques. RNN, LSTM, GRUs, all these, these can also be used for time series purpose. But you also have very advanced NLP techniques which have come to light now, wherein you have sequence to sequence models, attention mechanism, transformers, GPT models, BERT models, and bunch of things. And once you know all these things, you'll also understand about building your chatbots using RASA NLE. And many other things is what you learn, like GANs, reinforcement learning, autoencoders, variational autoencoders. How do I automatically generate images? Automatically, how do I generate text? All that. Okay, but that would be part of your professional certificate program in data science and AI. Now let me download the Python code. And let's quickly run through the recurrent neural network code. So what I shall do is, I would open a new notebook. Okay, and then come up. I'm going to change this as RNN, TensorFlow, Keras. Okay, I'll change the runtime to GPU, and I want a high RAM. I'll save it. Let me connect. Okay, I'll terminate all these sessions which exist. Yeah, so that we may connect. And while this connects to the server, let's go to download folder, RNN, and let me get this out. So first thing is, we need to load the required libraries. So we are importing simple RNN. We are coming up with something called a sequential and embedding. Embeddings means like one-hot encoding, wherein you convert your words into numbers. Embedding also converts your words into numbers. In a slightly different manner, it does it. You learn about this in the other, in your professional certificate program in data science and AI. So what we are doing is, we are saying, I want to have a sequential model. Okay. And I want every word to be represented in this dimension of 10,032. And then you want to take that data and you want to supply it to 32 RNN units. Run it. Come up, yeah. So you have 32,000 parameters that your model learns as part of embedding. Okay, and you have again RNN, which has 2080 parameters. So let me add a new line of code. Okay. So let me do one thing. What's the time? Okay. I'll do one thing. I want to spend some more time, and then explain in detail at least a few aspects, so that it's clear before you proceed further, if at all you are part of professional program, right? So for that, I'll do one thing. I will just pause here. So after that brief pause, we would be moving on to the next level. So I thought I'll spend just some sweet amount of time, short, considerable amount of time in explaining this, right? So you have two things here. One is called as samples. Another is called as dimensions. Okay, what this means. If you have a specific word of English vocabulary, if you were to do a one-hot encoding, if you have a specific word of English language, say that word happens to be beautiful. And say you want to take that word and analyze further, the first thing that you do is you convert that word into one-hot encoding. Because you cannot supply the words as is to your RNN, so you convert that into one-hot encoding. In English language, you have approximately 172,000 words. So you take all those 172,000 words, all those words, and then wherever you see this word beautiful, against that word, put a 1. For rest of the words, it would be all zeros. Okay, for all the other words, it will be zeros. But here you'll have, it is called as a dense dimensions, right? You have far too many dimensions. Or I would call it as not dense, I would call it as sparse. A lot of zeros exist and only one number exists. This was considered to be ineffective way of dealing with textual data because a lot of values would be zeros. To counter that, people have come up with yet another way of converting these into numbers, and that's called as embedding. Word embeddings, you have again pre-trained models in this. All that finer details you learn as part of your professional program, friends. Here for a certificate program in data science, we won't get into that depth, okay? So you're saying that instead of representing each word using 172,000 numbers, you want to represent each word using 32 numbers. And you're saying you want to use maximum of 10,000 words. If you have a specific document, that document might contain more than 10,000 words. If you have more than 10,000 words, you're saying cut off and take only the 10,000 words which are most frequently used, and then convert those into some numbers of 32 dimensions. I mean, each word would be represented using 32 numbers. Okay, that's what we're doing here. And there is another thing that we're doing here, and that is if you use return underscore sequences, just a minute, sorry. Oh, sorry about that. So here, if you do not have return underscore sequences, what would happen is the results would be displayed here itself. Results will get displayed immediately. But if you feel that I don't want the results to be displayed immediately, I want all the results to be carried forward like this. And I want only the output to come out here. Then you use this return underscore sequences, and wherever you do not use that, that is where the output would come out. That's the difference, friends. That is the difference. Okay, next. With respect to return underscore sequences. Then what we are doing here is we are loading the required libraries. That is, from Keras datasets, we are taking Internet Movie Database, which has movie reviews. Okay, all the movie reviews which are returned would be available here. And then you're importing sequence. I'll tell you what it does. And you're saying maximum features means maximum words you want is only 10,000. If something has more than 10,000, you want to ignore that. And maximum length equal to 500 means you want only 500, sentences. Am I right in saying this? Okay, yes. So what you're saying is, okay, now let me explain. This IMDb has movie reviews, friends. Data pertaining to movie reviews. And then you are, say, in movie review 1, you have 500 words. In movie review 2, you have some 20 words. In movie review 3, you have some 8 words. Movie review 4, you have 1,000 words. Someone has written it in the review. And now if I take all the words, all the unique words, if I take all the unique words, word 1, word 2, word 3, word 4, word 5, in that way, say you got some 30,000 words, 30,000 unique words. And then you count how many times each word appears. Each of these 30,000 words, how many times did it appear? Maybe here also you use the word beautiful. Here also you use the word beautiful. Here also somewhere you use the word beautiful. So beautiful appeared 3 times. In that way, count how many times each word appears. Take the count also. So you'll have words. And then you'll have count. And then sort this. Sort this in descending order. When you sort this in descending order, then you might want to just cut it off, saying that out of all these, I want to use only the top 1,000 words. So this 1,000 represents those words which have been used maximum number of times. That's this 1,000. Now here you also have something called as max length equal to 500. So all you're saying is, if this review has say 1,000 words, cut it off at 500 words. Okay. If this review has 2,000 words, cut it off at 500 words. Cut off each and every review at 500 words only. But what if I have a review for some 10 words? If you have a review for 10 words, then to get 500, you need another 490. You have only 10 words. To get 500, you need to add another 490 words. You do padding. That means you put all zeros. That's called as padding. And that is what is given here. Pad underscore sequence. The sequence, pad it, is what you're saying. Maximum length you want is 500 for every review. And all the words of all these reviews put together, unique words, sort them and take only the top 1,000 words which are most frequently used. Batch size is 32. This print statement only says that, okay, data is getting loaded, ... Whatever is in this, the same thing gets displayed here, but I would rather remove it. Doesn't make sense, right? So from IMDb dataset, you're loading the data, and when you're loading itself, you're saying the number of words that I want is only 10,000, which is maximum features. Okay. Then you're printing the length of input data, length of input test data, training data, and you want to see the padding sequence. Right? And you're saying if there is any review input in the training data, if there is any review, which is not of 500 words, then pad the sequence. In the test data also, if you do not have, pad the sequence, then print the data here. So the data is getting loaded. Then you have 2,500 training, so 25,000 training sequences, 25,000 test sequences, those many reviews, right? And then if you look at the samples into time, that's a padding sequence, you have 25,000 reviews and each review is having 500 words. Then test data also, you have 25,000 reviews and 500 words. That is data pre-processing that we have done until now. Then you import the dense network. You're creating a sequential model. You're saying that first, I will take all the words, all these 10,000 words, okay? And I'm going to have each and every word represented using 32 numbers. Every word, 32 numbers. And I want to run a simple RNN network, 32 units of RNN I need. That means one unit, second unit, this is third unit, everything is called as a unit. And then you're connecting the results to a dense network with one single neuron and you're using sigmoid activation function. Run it. And then we are also compiling a model because we want to know whether a movie review is positive or negative. What is the sentiment? If you want to analyze a movie review and tell whether it is positive or negative, then it's two-class problem. Hence, you need a single neuron in the output layer. And do not forget, please, at any cost, this particular thing that we have been referring to time and again. If I want to take a movie review and classify whether the movie review is positive or negative, then it's a two-class problem. If you have a two-class problem in the output layer, you might have a single neuron. And the activation function would be sigmoid. And cross optimization function would be, or the last function would be binary cross entropy. You have binary cross entropy and accuracy. Then you are fitting your model. While you train your model, you're saying, I want to train my model on the inputs and output of training data. I want 10 epochs. Batch size is 128 and validation split is 0.2. That means 20% of the data I want in validation. So I run it. And the number of epochs are running. So is it taking too much of time? Yes. Not the GPU is not getting triggered. I'd be surprised if that is the case. No, GPU is enabled. Despite having the GPU, is it taking so much time? Then I'll be pleasantly surprised. Anyway, so that's how your recurrent neural network is anyways. But probably the GPU, which is assigned to me on Google Colab, is a small configuration one. That is the reason why each epoch is taking so much of time. But then I'll quickly explain what we are trying to do here. After a single epoch, I'll explain. So here, in this object called history, or if I were to change this to model, what will happen is, within the model, or that's okay, any object name you can give it. Within this object, you'll have something called as history. History has accuracy details, okay? And this history has validation accuracy, and this history has loss. This history has validation loss. So all four: loss, accuracy, validation loss, and validation accuracy are there. You're taking all those values and you're importing matplotlib. Then what you're doing is you're saying, let me plot epochs, 10 epochs, right? So you're saying range of 1, accuracy plus 1. Whenever you say range in Python, when you say range of 1, 10, it will give 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 it doesn't give. Okay. That is why you're saying length of accuracy. You'll have 10 different accuracies because you have 10 epochs, plus 1 is 11. If you have until 11, then it will print until 10. So those are epochs. Those will be on your x-axis. So number of epochs here. And on your y-axis, you want the accuracy values to be printed. And you want blue color circles. And you want to give it a label called training accuracy. And on top of that, you want to do another plot, wherein again on x-axis, you'll have epochs. On validation and on y-axis, you'll have validation accuracy. V means you want a blue line. You want to label this as validation accuracy. Overall title name should be training validation accuracy. And when you say show me the legend, it will say that blue color circles will be training accuracy. Blue color line will be validation accuracy. Okay, that is how we want to run it. So either we wait for another 10 minutes because this execution would take, each epoch is taking approximately, 77 seconds, so just above a minute. So maybe it would complete the remaining epochs in another, I should say 10 minutes, right? So we would wait for 10 minutes for this to get completed, and then we will just run these 2 lines of code. And with that, we can conclude. So I'll stop here for now. So our 10th epoch is in progress. It is on the verge of completing the number of epochs. And if you see on the, accuracy front, accuracy has been increasing epoch after epoch. And the validation accuracy has been fluctuating a bit, decreasing, accuracy was decreasing and increasing, so on and so forth. But let's see after the final epoch, what would be the status. So once this is done, we would run this piece of code. Yep, it's done. So if you run this piece of code, it will tell you on whether your model is overfitting or underfitting. And you can run for more epochs, of course. We have run for only 10 epochs because it was taking huge amount of time, but otherwise you can run your algorithm for huge number of epochs and see after how many epochs is it overfitting. I see that after 2 epochs, probably the training accuracy and validation accuracy is just getting, the distance between accuracies is increasing. The difference between the accuracy values has been increasing. So you can also do the same run for the loss also, and then figure out, and you can easily figure out that after 3rd epoch, the training loss versus validation loss have been increasing. And the difference between these 2 has been increasing substantially. So this is all we had. So let me tell you clearly that you have certificate program in data science. All that has been explained has been more than what has been promised. And all these recorded videos would be on your learning management system, which is AI Spry. And you will find these under recommended videos. Please watch it, and the required training slides and the code is anyways available for you guys on learning management system. Make best use of that. These videos of neural networks is mandatory for you all to proceed further with professional certificate program in data science and AI. We call this as PDS program. Okay, and in this PDS program, you will understand about self-driving cars, how computer vision and neural networks has been used in that, pre-trained models, explainable AI, When you have small set of data, how do you deal with that? You learn about advanced natural language processing techniques such as sequence to sequence, attention mechanism, transformers, BERT, GPT, etc. Alongside LSTM, GRUs, bidirectional, deep bidirectional, one-dimensional convolution networks. You learn about OpenCV in computer vision. You learn about object detection models such as mask RCN and fast RCN and fast RCN and YOLO models. You learn about autoencoders, variational autoencoders. You learn about generative adversarial networks and the various variants of GANs, wherein give a text and then it will automatically generate the image for you. If you type frog, it will generate frog. How to automatically generate text, how to automatically generate images. Reinforcement learning or Q learning, which is used in solving the most advanced business problems today in the world, would be learned. You'll learn how to build RASA NLU. You will understand about auto ML, auto keras, right? Which is one of the beautiful libraries which will help you perform a lot of things automatically. And many more. DBNs, RBMs, right? DBNs, then speech related, and many other things. So thank you all so much for paying attention and patiently listening to me. And the RNN PyTorch code, if you're wondering on where is that, okay, that would get covered as part of your PDS training. So thank you so much, friends, for paying attention, and whatever you have learned would certainly help you immensely on two aspects. One is for clearing your interviews. And in most cases, I will not be surprised if your interviewers have less knowledge than what you have. Everything is taught. It's your turn to put in the hard work. Okay, and also in handling the projects. This will help you immensely. Thank you once again, friends. And it has been a real pleasure and honor, teaching you all. Thank you once again and have a great day. Bye. And all the best for your future.